pivot into what I want to talk about today. And so what I want to do is I want to do a discussion about acids and bases. Now, we're not going to go into acid-base imbalances quite yet. This is kind of the foundation because we need to understand what an acid is and what a base is, how we measure acid concentration and so on. And once we understand that, then we're going to talk a little bit about chemical reactions. And then what we're going to do is we're going to talk about molecules, right? Because now we have chemical reactions, molecules, and then we're going to talk about complex molecules, or what we call macromolecules, and some of the important biochemical pathways within the cells where these macromolecules are used. And we will even talk a little bit about what happens in states where the cells are hypoperfused, and that can be due to various reasons. But when you have a hypoperfused cell, what does that do to these pathways? And these pathways are not working. And what are some of the chemical and biochemical consequences? So we're going to, look at some of the chemical consequences, and that'll allow us to begin to understand how that translates to the consequences to the tissues where there's hypoperfusion, the organs, the organ systems, and ultimately the organism, like what we actually see with the person and the signs and symptoms and some of the lab tests. So you can see we're kind of taking this bottom-up approach, and we'll even do some top-down. So we're kind of looking at this in multiple different directions. So what I'm going to do is I'm going to go in and I'm going to share my notes with you all here. And we're going to talk a little bit about acids, bases, and what they are and what's going on there. So go in here and let's just start a brand new note. All right. So let me ask you all the question. What is an acid?
Based on the pH scale, it would be below the body's normal, which would be below 7.35.
So maybe an acid has something to do with the pH scale. Okay, maybe. Under a pH of 7.35, possibly. But what is an acid? Like when you say acid, like what does that actually mean?
Is that an electrolyte?
Maybe. So what are electrolytes again? What are electrolytes? We talked about the meaning of a definition of electrolyte yesterday.
It dissolves in water.
When what dissolves in water?
A compound between a metal and non-metal.
It's the hydrogen ions.
You're moving in the right direction.
It's an essential mineral, like salt or something.
Maybe. So remember we talked about this yesterday in electrolyte. So remember I talked about the concept of an ion, right? Let's review this. What is an ion?
The positively charged electron, I guess.
You're moving in the right direction. So an ion is an atom or molecule that takes on a charge. This is critical for understanding stuff a little later on. So an ion is something that takes on a charge, right? Either gains or loses an electron. All right. And there are two major categories of ions. There are what we call cations, and cations are positively charged. All right. So when sodium loses an electron, for example, and becomes Na+, that is a cation. Now, elemental sodium, right, just sodium that has not undergone an ionic or has not undergone a chemical reaction to turn into an ion, is not an ion or a cation. It is the positively charged sodium. Potassium, K+, would be considered a cation. Magnesium, Mg+2, calcium, Ca+2. Those are all cations, okay? Anions are negatively charged atoms or molecules. For example, when chlorine becomes chloride because it accepts an electron, right? That would be an example of an anion. When fluorine becomes fluoride, that would be an example of an anion. All right. When ions dissolve in water, they are called electrolytes. All right. So an electrolyte is an ion that is dissolved in water. All right. So when somebody mentioned that maybe acid has something to do with electrolytes, you're moving in the right direction. And then somebody mentioned hydrogen.
Yes, sir. It's when most of the acids have to have hydrogen in them.
You're moving in the right direction. It may have something to do with hydrogen. Yeah. Okay. So we kind of, it seems like you all kind of have a basic intuition. You're like, well, it's kind of like this, it's kind of like that. What I want to do is I want to plant a flag there, and let's drill down and really get an understanding for what acids are. And it's not incredibly intuitive, and there are actually multiple definitions, right? And so what I do, I want to talk about the main definitions of what an acid is, all right, and what a base is, all right. So there are very specific definitions and very broad definitions, and the most specific definition, and it is a definition that's been around since the late 1800s, and this is the first one, the first definition, which is very specific and somewhat helpful for us. And so this came out in the 1880s. A guy by the name of Arrhenius came up with this, and this is what he said: an acid will increase hydrogen ion concentration when dissolved in water. All right. So this is critical for us to understand. When we're talking about an acid, right, for something to be acidic or basic, water has to be involved. It has to involve an aqueous environment. If that's not the case, the concept of an acid just does not apply. So an acid will increase hydrogen ion concentration. So what is a hydrogen ion? Well, a hydrogen ion is a hydrogen atom. All right. So remember, hydrogen is a proton, is one proton and one electron, right? So a hydrogen atom is a proton that has lost its electron. And so you just have a proton by itself, right? A proton by itself is what's known as a hydrogen ion. It's ionized hydrogen, right? So we often symbolize this with an H plus, all right? H plus equals hydrogen ion, also known as a proton by itself, right? These are all equivalent statements. So an acid will increase hydrogen ion concentration when dissolved in water, all right? So that's kind of what Arrhenius came up with. And then a little later on, so about 30, 40 years later in the 1920s, a more robust definition for acids and bases, for that matter, came up. And these are two guys named by the name of Bronsted and Lowry. I believe they were Swedish. At least one of them was a Swedish physical chemist. BL is sometimes how this is symbolized. Bronsted-Lowry came up with another definition. And Bronsted-Lowry is the major definition for acids and bases that we're going to use. I'm going to talk about another one. It's much more complex. It's very inclusive. It's a lot more complicated, and it's not quite as helpful for us. So we're going to stick with Bronsted-Lowry for the most part. But what Bronsted-Lowry says is an acid is anything that donates. I'll put that in quotes. So donate, you can think of as giving off, right? It gives off, it releases hydrogen ions when dissolved in water. That is the Bronsted-Lowry definition of an acid. And then a base is anything that accepts hydrogen ions when dissolved in water. All right. So that is a Bronsted-Lowry definition. Now, there is another definition. This is actually an American chemist by the name of Lewis. And this is actually a very complicated, very complete definition. And I'll just mention it briefly, but we're not really going to use the Lewis. And essentially what an acid is something that can accept a pair of electrons, right? So if it can accept a pair of electrons, then we would call it a Lewis acid, and a Lewis base is something that donates a pair of electrons. And in this case, it doesn't necessarily need to be hydrogen ions. Now, a hydrogen ion does meet the definition of a Lewis acid. So if you have a hydrogen ion, H plus, right, and then you say you have some atom that has a pair of electrons in its valence, that hydrogen ion wants to kind of get a hold of a pair of electrons to meet the octet rule. So it will accept, or it will interact with that pair of electrons. But other things can also meet the definition of a Lewis acid. For example, aluminum ions, Al+3, right? It's an aluminum that has lost 3 electrons, right? It can interact with, say, water. So if you look at a water molecule here, you've got pairs of electrons on that oxygen, and that Al+3 will interact with those pair. It'll accept those pair of electrons. And so that would be an acid by the Lewis definition. But with that said, we're going to focus on the Bronsted-Lowry definition. And for our purposes, we're going to say an acid is anything that gives off or donates electrons or releases hydrogen ions when dissolved in water, and a base is anything that accepts hydrogen ions when dissolved in water. Okay, that's what acids and bases are. For example, let's say that I have hydrogen chloride, HCl. A hydrogen chloride molecule. And I have a cup of water here. All right. So I've got water molecules, H2O, right? Remember, water is polar. So you're going to have the oxygen part is going to be more negatively charged, and the hydrogen parts are going to be more positively charged, those water molecules, because oxygen is more electronegative. All right. If I put this hydrogen chloride into the water, what's going to happen is the hydrogen is going to, because what happens here is the hydrogen has given its electron to the chloride, right? Because the chloride is very electronegative. And so what happens, so this is an ionic bond that we're dealing with here. So what happens is when a hydrogen chloride is dissolved in the water, those hydrogens, that it'll dissociate. The hydrogen, because it has lost an electron, it's going to be more positive. It is going to be attracted to the oxygen. So I put that hydrogen chloride, HCl, in the water, and then the hydrogen will pop off and it will be attracted to the oxygen. And then the chloride will pop off, the Cl minuses, and they will be attracted to the hydrogen part of the water molecule. And that hydrogen chloride will break apart. It will get dissolved. It will dissociate into hydrogen ions and chloride ions. And when that happens, we call that hydrochloric acid. Right? Because that molecule is donating hydrogen ions when it gets dissolved in water. The same thing with hydrogen fluoride, or HFL. If I put HFL into water, right, the same thing will happen. The hydrogen ions will break apart from the fluoride ions, and then hydrogen ions will be released. And so that will become hydrofluoric acid. Everybody okay there? Does that make sense?
I kind of got
Yes,
lost,
sir.
I'm not gonna lie.
Say that again, I'm sorry. Did someone, there confusion, or
Yeah, I kind of got lost there.
where at? Where's the confusion, or could you? Let's see if I can solidify the concept. Let me know where the confusion is, and I'll try to explain it maybe differently. I'm not sure I'm not sure who said that, but could you?
So it's the whole, basically, when you're giving away the proton, basically, is that like it becomes, that's where I'm kind of getting lost there.
So yeah, so what happens is anything that when you dissolve it in water, if it breaks down and gives up hydrogen ions, so if a molecule gets dissolved in water and hydrogen ions come out of it, it breaks apart, it gives off hydrogen ions, that's what makes it an acid. So when hydrogen chloride gets dissolved in water, it breaks apart into hydrogen ions and chloride ions. And because it is releasing the hydrogen ions, we call it hydrochloric acid. That's what makes it an acid. The same thing with hydrogen fluoride, HFl. When it gets dissolved in water, the hydrogen ions pop off. It is the release of these. So this hydrogen atom here becomes a hydrogen ion, and that's what makes it an acid, just like here. Does that make a little more sense, or?
Yeah, that one kind of elaborated on more. I think the drawings are the ones that are messing me up there. But yeah,
Okay.
I understood that way better.
Okay, yeah. And this drawing here is explaining why that happens. Because remember, yesterday we said that water is a polar molecule, right? So the H2O molecule kind of looks like this. And the oxygen part of the molecule is more negatively charged. And the hydrogen part of the molecule is more positively charged. And so when that hydrogen chloride gets dissolved, the hydrogen ions are attracted to the oxygen part of the water, and the chloride ions are attracted to the hydrogen part. But it is the fact that the hydrogen chloride is breaking down and giving off hydrogen ions, that's what makes it an acid. So if this over here is a little easier to understand, it's just as correct. In either way, as long as you understand that the molecule is giving off hydrogen ions, that's what makes it an acid. All right. Now, with that in mind, there are different kinds of acids. There are what we call strong acids, and there are what we call weak acids. And a strong acid is something that 100% of the time it will break down fully. So hydrogen chloride or hydrochloric acid is considered a strong acid. So every single molecule of HCl will break down when you dissolve it in water. So every molecule of HCl will give off a hydrogen ion 100% of the time. Weak acids, only part of the molecules will give off hydrogen ions. So a weak acid, maybe you put 100 molecules of a weak acid in water, and 60 of the molecules give off hydrogen ions, but 40 of them do not, right? So it only partially dissociates, and so that's what makes it a weak acid. In both cases, they're giving off hydrogen ions, but it is the percentage, right? A strong acid, like hydrochloric acid or hydrofluoric acid, 100% of the time, every molecule will give off a hydrogen ion. Whereas with weak acids, it's only a certain number of those molecules will give off a hydrogen ion. And that concept we will dive into that concept a little later on when we talk about organic acids. So far, we've only talked about inorganic acids. In organic, does anyone know what organic means in terms of chemistry?
It has carbon.
Yeah, so organic in terms of chemistry means that carbon forms the backbone of the molecule. So you see like hydrochloric acid, for example, it doesn't have any carbon in it at all. And so it is what we call an inorganic molecule. Whereas organic molecules are going to have carbon that forms the backbone of them. We haven't talked about that, but we will a little later on today talk a little bit about organic chemistry. But inorganic is a little easier to understand as far as acids go. So is everybody okay on what an acid is? An acid is a molecule that when dissolved in water gives off hydrogen ions. It may be strong or weak, but either way, that's what an acid is. And a base is something that will accept or take a hydrogen ion when dissolved in water. For example, if I have bicarbonate ions, if I have, or you know what? No, let's do this. If I have sodium bicarbonate, so NaHCO3, that is a molecule of sodium bicarbonate. This is also known as baking soda. All right. If I take sodium bicarbonate, and let's say that I have a glass of water here, and I dump sodium bicarbonate into the water, sodium bicarbonate is going to break down into sodium ions. So the sodium is going to pop off, and bicarbonate ions, HCO3 minuses, like that. Okay, so when I put sodium bicarbonate in water, it will break down into sodium ions and bicarbonate ions. And then what will happen is if there are hydrogen ions floating around in that water, the bicarbonate is attracted to the hydrogen ions, and the hydrogen ions are attracted to the bicarbonate. And so the HCO3 can combine with the hydrogen ions. It will accept, right? It will accept those hydrogen ions, and it will form a new molecule, H2CO3. All right. So the bicarbonate accepted the hydrogen ion to form a new molecule. And so sodium bicarbonate would be considered a base because it is accepting hydrogen ions instead of giving hydrogen ions off. So bases, when dissolved in water, accept protons or hydrogen ions, and acids release or donate. Is everybody okay there? Does that make sense?
So it becomes H2CO3 because it accepted the other hydrogen, correct? Instead of having
Yeah,
like
so the
one single hydrogen.
Yeah, so the HCO3 combined with the hydrogen is like, hey, come on over here. And so now you have two hydrogens instead of one. So it becomes H2CO3 instead of HCO3. Yes, absolutely. You got it.
Boom.
Nailed it. All right. Excellent. Okay, so now here's the question. Now that we know what an acid and a base is, now the question is, how do we measure acids specifically? We need some way of measuring. And the way that we measure is a little complicated. And we're going to talk about it because it's so important. It'll be important in pathophysiology. It'll be important in definitely important in pharmacology. So this is the concept, and this is going to go back to the periodic table of elements. And this is the concept of something called Avogadros number. Avogadros number. This is a very special number. It's a massive number. It is so large that I'm going to use something called scientific notation. And have you all heard of that term, scientific notation?
No.
No. Okay. Scientific notation is a way of, it's a shorthand. It's a way for us to make large numbers, very large and very small numbers, more manageable. Okay. And basically what it does is it says, okay, how many zeros do I have? For example, let's say that I have 100. I have 100. Now, that's not a huge number, but we're going to start with that. So if I have 100, I can rewrite 100 a little differently. What I can do is I can say, how many tens do I need to multiply to get to 100? All right. So how many tens do I need to multiply to get to 100? What do you all think?
10 tens.
Yeah. Well, not 10 tens, but
Are you saying 2 tens?
2 tens. Yeah. So I add 10, but if I multiply, I need 10, right? So 10 multiplied by 10 equals what? What does that equal?
100.
100.
All right. Woo, you guys are worrying me there.
Be
10
10 to the
times
1.
Yeah, so 10 times 10 is 100, right? So I need 1 10, 2 tens. I need to multiply tens to 100. Does that make sense? Everybody okay there? So another
Yes.
way I can rewrite 100 by saying that 100 equals 10 to the second power, 10 to the 2. So if you see 10 to the 2, that just means 10 times 10, right? Everybody okay there?
Yes, sir.
Okay. So let's say instead of 100, I have 1,000. How many tens do I need to multiply to get to 1,000?
So you're gonna go
3,
100 to the
3.
second power?
10 power 3.
Yeah, so I need 10 times 10
3
times
tens.
10. Good. So 1,000 can be rewritten as 10 to the third, right? 10 to the 3 equals 1,000, right? 10 times 10 times 10. What about 10,000? How many tens do you need?
4.
10 to the 4. What about 100,000?
5.
10 to the 5. Good. What about 1,000,000? 10 to the 6, right? So every time I multiply 10 by 10 by 10, I get 10 times larger, right? So 1,000 is 10 times larger than 100, right? 10,000 is 10 times larger than 1,000, right? 100,000 is 10 times larger than 10,000, all right? So 10 to the 2, 10 to the 3, 10 to the 1, right? 10 to the first power is just 10, right? Because, right, you just have 1 10. And then, interestingly enough, 10 to the 0 power equals 1. And I can do the same going in the other direction for numbers smaller than 1. For example, 0.001 can be rewritten as 10. And because the decimal point is moving in the, well, I guess on your screen, I should go that way, in the opposite direction. So here's 1, 10, 100, 1,000, right? So we got 1 is 10 to the 0, 10 is 10 to the 1, 100 is 10 to the 2, 1,000 is 10 to the 3, and so on and so forth, okay? So here, 0.1 would be 10 to the minus 1. And then 0.01 would be 10 to the minus 2. The decimal point is boop, boop, move, or boop, boop, moving 2 places over. 0.001 would be 10 to the minus 3, and so on and so forth. All right. Is everybody okay there? Does that make sense?
Yes, sir.
Okay, that's what scientific notation is a way of rewriting very large and very small numbers. So going back to Avogadro's number is a massive number. It's so large that we just write it in scientific notation, and it is 6.02 times 10 to the 23. So that decimal, so that's 6 with 23 zeros behind it, essentially. That's how large of a number it is. So it's just too large to write. So it's 6, and then this decimal point moves over 23 times, and whatever that is, that is what Avogadro's number is. 6.02 times 10 to the 23. All right, everybody okay so far?
Yes, sir.
Cool. Now, this number has another name, and the common name is something called a mole. A mole. So a mole equals Avogadro's number. Okay. Equals 6.02 times 10 to the 23. So if I have a mole of something, right? If I have a mole of pennies, I have 6.02 times 10 to the 23 pennies. That's what a mole is. It equals Avogadro's number, equals 6.02 times 10 to the 23. Why is this? Why are we even talking about this? Well, this is why. I'm going to stop sharing on my iPad here, and I'm going to bring up the periodic table elements on Canvas. And what we're going to do is make sure you all can see this. This started screen sharing. Ah, there we go. All right. Remember yesterday how I talked about, so the integer number there above the hydrogen, that 1, that's the atomic number, that's the number of protons. But remember the number down here, which is not, is the decimal number, the 1.008 here. That is called the atomic mass. Now, here's the crazy thing. And this allows us to convert atoms into concepts that we all understand a little more intuitively. Every single element has a different atomic mass. So let's just look at hydrogen. Hydrogen has an atomic mass of 1.008, or basically 1. Here's the cool thing. If I have an Avogadro's number of hydrogen, I will have its atomic mass in grams. So if I have 6.02 times 10 to the 23 individual hydrogen atoms, I will have 1 gram of hydrogen. Likewise, if we look at sodium here, sodium has an atomic mass of 22.99, so 23, right? If I have an Avogadro's number of sodium, a mole of sodium, 6.02 times 10 to the 23 atoms of sodium, I will have 22.99 or 23 grams of hydrogen, right? Likewise, if I move over to carbon here, if I have a mole of carbon, I have approximately 12 grams of carbon. Is everybody okay there? Does that make sense?
Yes, sir.
Okay, cool. So I'm going to go back to the iPad, and we're going to talk about how that actually relates to hydrogen ions, because that's what we're trying to do, is trying to figure out how we can measure acid base. All right, so we start. There we go. Let's go back to the lecture here, or the notes. So we know what all that means. Moving right up. Okay, so here's the thing. If I have 1 mole of hydrogen ions, how many grams of hydrogen ions do I have?
1.008.
Yeah, so I have approximately 1 gram of hydrogen ions, right? So if I have a liter of water, so I have 1 liter of water, of pure water, of distilled water, all right, and I dissolve 1 mole of hydrogen ions in that water, I would have 1 mole per liter. Okay. Here's the thing. That is such an incredibly high concentration of hydrogen ions that is incompatible with life. It is impossible to have that many hydrogen ions dissolved in a liter of water, let alone have that kind of concentration in the human body, right? So typical concentration of hydrogen ions in the human body is going to be something like, so remember, 1 mole is 6.02 times 10 to the 23, right? And a typical concentration of hydrogen ions in the body is going to be something like 10 to the -7 moles per liter. All right. That be a reasonable number that you would see. Even that is actually not really compatible with life, but it's a bit more reasonable. All right. So here's the problem that we run into. This is very difficult to understand, right? If someone came up to you and said, your patient has 10 to the -7 of 6.02 times 10 to the 23 hydrogen ions dissolved in their blood plasma, what does that mean to anybody? Does that mean anything to any of you? So you have a tiny fraction of a very large number. What the intuition just completely fails. And so what we do is we do a little trick. So what we do is we take the molar concentration of hydrogen ions, all right? Let's say that I have 10 to the -7 moles per liter, all right? Now, what I can do is I can take what's known as the logarithm. I can take the log, and a logarithm is essentially asking how many factors of 10 are in the number, right? So for example, if I had 10 to the 7, not 10 to the -7, but if I have 10 to the 7, and I take the logarithm base 10 of 10 to the -7, taking the log of something is just asking how many multiples of 10 are there? So the log base 10 of 10 to the -7 would just be 7, right? Because there are 7 10s in there. Does that make sense?
Yes.
Okay. But here we are dealing with 10 to the -7, which is 0.1, 2, 3, 4, 5. right? 0.00007 moles per liter, right? So instead of taking the log base 10, what I will do is I will take the negative log base 10. All right. So if I take the negative log base 10 of 10 to the minus 7, the cool thing about taking the negative logarithm of a negative number is the negatives cancel out, and I just get a number 7. All right. So 10 to the negative 7, if I take the negative log of that, that just gives me a number 7. All right. If I have 10 to the negative 8, and I take the negative log base 10, that gives me 8. If I have 10 to the negative 6, and I take the negative log of that, that gives me 6. 10 to the minus 5, that gives me 5. 10 to the minus 4, that gives me 4. 10 to the minus 9, that gives me 9. And here's the cool thing. The negative logarithm base 10 of the hydrogen ion concentration in moles per liter is what we refer to as the pH. That's what pH is. pH is just a fancy way of rewriting the molar concentration of hydrogen ions in a way that's a little easier to understand. All right. And that's literally what pH means. It means the power or the potential of hydrogen ions, the power potential of hydrogen. That's pH. So pH is a way of measuring acid, right? And so this is the pH scale. And the closer I get to 0, the more concentrated the hydrogen ion concentration is, right? Because 10 to the minus 4 is a larger number than 10 to the minus 7. In fact, every step on this scale is an order of magnitude or a multiple of 10. So 10 to the minus 6 is 10 times more acidic than 10 to the minus 7. So a pH of 6 is 10 times more acidic than a pH of 7. Right? A pH of 5 is 10 times 10 or 100 times more acidic than a pH of 7. A pH of 4 is 10 times 10 times 10 is 1,000 times more acidic than a pH of 7. Whereas a pH of 8 is 10 times more basic than a pH of 7. pH of 9 is 10 times 10 or 100 times more basic than a pH of 7, right? Moving in that direction. So this is a pH scale, and generally we say that it runs from 0 up to 14. So a pH of 0, right, would be what? Well, that would be 10 to the 0 or 1 mole per liter concentration of hydrogen ions. Whereas 14 would be 10 to the minus 14 moles per liter, right? A tiny, tiny concentration. And then in the middle, 7 would be 10 to the minus 7. And where does normal human pH? What's the normal pH for
Between
humans?
7.35 and 7.45.
Yeah, so it's It's a bit more alkalotic than 7. So it's kind of right in here is where we see, right? So between 7.35 and 7.45. In fact, perfectly normal human pH is 7.4. 7.4 is perfectly normal. All right. Does that make sense? What pH is, what acids are, what bases are? Is everybody okay there?
Sir. Yes, sir.
Okay, okay. So it's a little more complicated than you might originally think, but hopefully that makes sense now. Okay, so that's what pH is. That's what it measures, right? It's just it's a way of recontextualizing or rewriting the hydrogen ion concentration. So the next thing I want to do is I actually just want to do a quick little exercise to show you how the concept of a mole actually works in physiology. And let's just take another concept. And let me ask you all, as I understand, most of you are EMT intermediates in New Mexico, is that correct?
Yeah.
Yes.
Okay.
Yes.
So you all would consider yourself experts in IV therapy, right?
No.
No.
No. That's like a fundamental, that's a fundamental part of what you do as an intermediate is you administer IV therapy, right?
Yes, sir.
Specifically normal saline, right? You guys can normal saline.
Yes, sir.
Okay. Let me ask you a question. What does normal saline have in it?
Sodium chloride, 0.9%.
Okay. Yeah, it has sodium chloride, 0.9%. What the hell does that mean? What does that really mean?
I mean, it's 0.9% of sodium chloride in 100. So sodium chloride is 0.9% out of the total 100. The rest is liquid. So water could.
You're moving in the right direction. Yeah.
So that's the concentration.
It is a concentration. And in pharmacology, whenever you see percentage, this is something that I want you to all remember. Percentage in pharmacology, in physiology, is always grams out of 100 milliliters. Is everybody okay there? So if you have a drug that's 1%, a 1% concentrated drug, that should mean that there would be 1 gram of that drug dissolved in every 100 milliliters. That's what 1% is. 10% would be 10 grams in 100 milliliters, right? So if you administer, say, dextrose, D50W, for example, right? 50% dextrose, there would be 50 grams of dextrose in every 100 milliliters, right? So with sodium chloride, if it is 0.9%, there should be 0.9 grams of sodium chloride in every 100 milliliters of IV solution. So let's see if we can prove that. All right, let's see if we can prove that with the chemistry knowledge that we have. So when I look at a bag of sodium chloride, let me share a picture that I have pulled up with you for you all. Let's look at the sodium chloride here. No, I want the sodium chloride. There it is. Let me share that with you. If you can see that. It doesn't look like it's pulled up quite yet. There we go. All right. So we look at the sodium chloride here. you can see right here, it says approximate millimoles per liter, sodium 154, chloride 154. Everyone see that there? And this is a new concept that I'm going to talk about. And this is a concept of a milliequivalent. This is a concept of milliequivalence and equivalence. So an equivalent is how we measure electrolytes. That's how we measure electrolyte concentration, right? Now, in some sense, you can say an acid is an electrolyte because it involves hydrogen ions, but it's very special. And so we measure acid concentration with pH, but other electrolytes we measure with something called an equivalent. An equivalent takes into account two things. It takes into account the electrical charge and the molar concentration. So moles times charge equals equivalent per liter. So if I have 1 mole of sodium ions, all right, dissolved in a liter, right? So the number of moles is 1 times the number of charges 1, and that equals what? 1 equivalent per liter. If I have 1 mole of magnesium ions, right? So I have 1 mole of magnesium times a charge of 2, that equals 2 equivalents per liter, all right? Now, what we can do here is instead of talking about just moles or just equivalents, I can talk about something called an MEQ, a milliequivalent. And a milliequivalent is just 1/1000th of an equivalent, okay? So 1/1000th of an equivalent is a milliequivalent. So that says that there are 1000 MEQ per EQ. So 1000 milliequivalents equals 1 equivalent, like 1000 milligrams equals a gram, or 1000 grams equals a kilogram. All right. So we're just breaking an equivalent up into 1000 parts. So when I look at that IV bag, I notice that it says there are sodium 154 MEQ per liter sodium ions, and there are chloride ions 154 MEQ per liter of chloride ions. All right. So let's just do some basic math and then we'll take a break here. So let's look at sodium first. So if I go to the periodic table of element, what is the atomic weight for sodium, or the atomic mass of sodium? Someone tell me what that is.
22.990.
22.990. So let's say that there are 22.9 grams per mole of sodium. All right. And let's look up chloride. What's the atomic weight for chloride?
35.45.
35 point, I think it's like 4.5 or 4 and some change. So let's just do 35.45 grams per mole. Everybody okay there? Now, on that IV bag, what I have is I don't have 1 mole of sodium or 1 mole of chloride, but rather I have 154 milliequivalents, which is 0.154 moles, right? Remember, equivalent is 1000 milliequivalents. So 154 divided by 1000 gives me 0.154. And because the charge is just a plus, +1, or -1, it's all equivalent. So what I'm going to do is I'm going to write a formula, and we're going to do a sodium first. Okay. We're going to do sodium first. So I know that if I have one equivalent of sodium, which is equal to 1 mole of sodium, if I have one equivalent of sodium, that's going to give me 22.9 grams, because one equivalent will be 1 mole. All right. And then I'm just going to write on the other side of the equation here. So this is what I know on this side. And on this side, this is what I want to know. I want to know how much sodium do I have if I have 0.154, right? And I got that from there, 154 divided by 1,000, right? 0.154.
You just cross multiply.
Yeah, so 0.154 equivalents, or 154 milliequivalents, and then X. How many grams do I have? So then this is just a simple cross multiplication, right? So 1 times X is X equals, and then 22.9 multiplied by 0.154 gives me 3.53 grams. So I have 3.53 grams of sodium per liter of normal saline. And then I'm going to do the same over here with chloride ions. So one equivalent of chloride ions is going to be 35.45 grams. And I have 0.154 equivalents, or 154 milliequivalents, X grams. And I'll do the same thing here. I'll cross multiply. 1 times X is X equals, and then 35.45 multiplied by 0.154 gives me 5.46 grams of chloride ions per liter. And then what I'm going to do is I'm going to add these up, right? Because this is sodium chloride. So I have 3.53 of sodium, and I have 5.46 of chloride, and that gives me a total of 8.99, or 9 total grams of sodium chloride per liter. All right. So 9 grams. All right. So I have 9 grams in 1,000 milliliters. All right. So what's 9 divided by 1,000? Or let's do this instead. 9 grams is how many milligrams?
9,000.
All right. So 9 grams is 9,000 milligrams in 1,000 milliliters. All right. Good. So that's equivalent saying. And we said that we should have 0.9% sodium chloride, right? That makes sense. And we said that percentage is grams in 100 milliliters, right? So I should have 0.9 grams, or 900 milligrams of sodium chloride per 100 milliliters. So is 9,000 milligrams in 1,000 milliliters the same as 900 milligrams per 100 milliliters? Are these equivalent statements?
Yes.
Yes.
Absolutely, right? So guess what? Using chemistry from first principles, we figured out, we basically converted what we saw in the IV bag, 0.9% saline, sodium chloride, the 154 milliequivalents and 154 milliequivalents, we were able to convert that to actual grams. So it actually works. It actually works out. And hopefully now you've learned something about a common IV solution that you give. You actually know how much actual sodium and chloride and where all this stuff actually comes from. All right. So are there any questions before we move on? We're going to take a break. Any questions? All right. I don't see anything there. Okay, so I've got what is about 9:52. Let's meet back up at 10:05. I will see you all at 10:05.
See.
Go. Okay, we're going to pick up where we left off and continue on. So now that we know what acids and bases are, how they're measured, what the concept of a mole is, and how it's relevant in a couple of different ways, we're going to pivot and we're going to talk a little bit about chemical reactions, because it is ultimately chemical reactions that are occurring within our body. And does anybody know there's a word that we use to describe the sum of all chemical reactions in the body? And does anyone know what that word is? It's the sum of all chemical reactions in the body. Does anyone know what that word is?
Is it homeostasis?
No. So homeostasis is essentially that's an important concept to pathophysiology, and that is the body is maintaining an internal environment that is separate from the external environment. That's homeostasis. And then alterations in homeostasis means that the body is not able to effectively maintain its internal environment. And so in some sense, it becomes more like the external environment, right? You go into a shock state, hypoperfusion, you get hypo or hyperthermic, something like that. Chemical reactions are involved in homeostasis because the body has to do lots of chemistry to maintain that internal environment. So these chemical reactions are critical for the maintenance of homeostasis. But this is a word, it means the sum of all chemical reactions in the body. It's a word that kind of encompasses everything. Does anyone?
Metabolism.
Metabolism, yes. Metabolism is the sum of all chemical reactions in the body. And there are two major types of metabolism in the body. Does anybody know what they are?
Anaerobic and aerobic metabolism.
That refers more to cell respiration. And that is, and we're going to talk about that, don't worry. That's how cells create energy, ATP, high energy phosphate molecules. And that can be done through anaerobic pathways, or pathways that don't require oxygen, anaerobic pathways that require oxygen. But with metabolism, there are two general types of metabolism. And most people, when you hear metabolism, a lot of people think, oh, the body's breaking stuff down, right? That's what most people intuitively think of when they hear metabolism. It's not the case. There are two types of metabolism. There's what we call anabolism. That is building, right? That is the body using chemical reactions to build new molecules. All right, building up. That's anabolism. And then there is catabolism, which is the body breaking things down. So breaking and building, breaking and building. Breaking is catabolism, building is anabolism. All right. Is everybody okay there?
Yes, sir.
All right. Excellent. Excellent. All right. Well, and let's move on. So I'm going to share Zoom again through the iPad with you all. I have some notes. We're going to talk a little bit about metabolism and a little bit about the chemical reactions involved. There we go. All right. Everybody can see that? Yeah. All right. So metabolism is the sum of all chemical reactions. And this here, this symbol, this is sigma. This is a capital S in the Greek alphabet. And anyone who has used Excel and spreadsheet should know what that means. A sigma function means add them all up, right? So whenever you see that, that means to take the sum of or to add everything up. So metabolism is the sum of all chemical reactions in the body. There are two types: anabolism, building up, and catabolism, breaking down. So the general way that a chemical reaction works, it doesn't matter if you're building or breaking, is you have reactants. So whatever is going to be involved in the chemical reaction, you have, those are called the reactants. Then you have the chemical reaction, and then what is the result of that chemical reaction is called a product. So reactants become products, right? And this can be building, right? So reactant A plus reactant B can be added together to form AB, right? A molecule AB, right? That would be a building, right? Or what we call synthesis reaction. You could also have AB, molecule AB breaks down into products A and B, right? Either way. Right? You start out with reactant and you end with products. Now, whenever you see chemical reactions, if you see a single arrow, an arrow in one direction, right? That means that that chemical reaction is irreversible. It cannot go in the opposite direction because the energetics are not favorable, right? It would take too much energy for that reaction to go up in the opposite direction. So if I have, for example, AB moving to A and B, so molecule AB undergoes a chemical reaction where it breaks down into A and B. And that arrow in one direction means that that's an irreversible reaction. Whereas double arrows means that that chemical reaction can go in both directions. It is reversible. So an example of that, going back to acid base, would be a strong acid. When a strong acid dissolves or dissociates in water, that is irreversible. It takes too much energy for the chemical reaction to go in the opposite direction. So when hydrochloric acid or hydrogen chloride gets dissolved in water, so these are the reactants, all right, that forms hydrogen ions and chloride ions. These are the products. And the arrow moves one direction. So hydrogen ions and chloride ions will not recombine to form hydrogen chloride once they're dissolved in water because it would take too much energy. It's not energetically favorable for that to occur. On the other hand, a very common chemical reaction in the human body is this one here, where carbon dioxide, right? And we know that cells produce, cell respiration, produce carbon dioxide as a waste. Carbon dioxide is a linear molecule, and it is nonpolar, and so it does not dissolve in water. So what happens is it has to be combined with water to form a new molecule so it will dissolve. So carbon dioxide combines with water to form a new molecule, H2CO3. This is also called carbonic acid. All right. And this chemical reaction can move in both directions, right? So these are the products, or excuse me, these are the reactants, and this is a product, right? But carbonic acid can also be converted back into CO2 and water. So that chemical reaction can move in both directions depending on the chemical environment, right? The pH of the environment, for example, or how many products do you have, or how many reactants do you have, can push the chemical reaction in one direction or another. It moves in both directions. The energetics allow for that to occur. Now, when we talk about general basic types of chemical reactions, you really have the major types. You have building, these are referred to as synthesis reactions, and the most common type of synthesis reaction is something called a dehydration reaction. Okay, so what you do is you take the reactants and you pull a water molecule out of those reactants, and that allows them to combine to form a new molecule, the product. All right. And a classic example of a dehydration synthesis reaction is where we take small organic molecules called amino acids, and we'll talk about those in a little more detail, and amino acids are combined. And amino acids actually form the basis of all proteins. And we'll talk about proteins because they're incredibly important macromolecules. But the building blocks of proteins are these small organic molecules called amino acids. And so what you have is you have an amine group on one part of an amino acid. Amine comes from ammonia, and ammonia is H3 and nitrogen with 3 hydrogens. That's ammonia. So the nitrogen containing group is what we call the amine. And then you have this acid over here. This is a special kind of acid, is an organic acid. And it is something called a carboxylic acid, or a COOH. So you've got C double covalently bound to an oxygen, and then you have a single covalent bond to an oxygen and a hydrogen. It's called a hydroxyl group. All right. So this is the amine part, and this is the acid part, and then you have this central carbon. This is called the alpha carbon, and you have some other chemical groups hanging off the end of that. And each amino acid has different side chains, right? So we have these 2 amino acids, and what they're going to do is we bring these amino acids together, and we want to combine the carboxylic acid part of one amino acid to the amine part of the other amino acid. So what we're going to do is we'll pull this hydrogen off and this hydroxyl group off. So I've got a hydrogen, and an oxygen, or I have H2O. So I pull that out of this situation during that chemical reaction. And what happens is that carbon, you can see here, that's this carbon, has now chemically combined with nitrogen, this nitrogen. And you can see that the H and the OH that we pulled out has formed a water. So we have dehydrated the reactants to produce a product. And this is known as a peptide bond, with the carbon bonding to the nitrogen in amino acids. And this is this forms the primary structure of proteins. And then we can add more and more amino acids to that. And that is something called a polymer. A polymer is where you have lots of molecules that you're combining together. polymers of long string molecules. It could be amino acids, it could be fatty acids, so on and so forth. So that's dehydration synthesis. And then the major breaking down reaction in the human body is called a hydrolytic reaction. So dehydration synthesize, you build with dehydration and you break down with hydrolysis. And hydrolysis means that a water molecule, okay, so you pull a water molecule, you break a water molecule down in the environment and add the water molecule to the chemical reaction. So here, up here, we're pulling a water molecule out. So we're dehydrating the reactants. But here, what we're doing is we are adding water, breaking a water molecule apart from the environment and adding it, right? So these are the reactants here, all right? And so this molecule here is actually a super common and very important molecule in the body called acetylcholine. Acetylcholine. This is an acetylcholine molecule, all right? And acetylcholine is an incredibly important neurotransmitter. And in order to terminate the action of acetylcholine, acetylcholine needs to be metabolized. In this case, it gets broken down, right? So up here, we're binding amino acids together to form proteins or peptides, but multiple peptides eventually will form a protein. Down here, we're breaking a molecule down. So we're breaking acetylcholine down into acetic acid here and choline here. So we're terminating the action of this neurotransmitter. And the way that we do that is right here. So you've got a CH2, CH2, OCCH3 here. We're going to take a water molecule here and we'll break the water molecule down into an OH and an H, right? So that's where the hydrolysis comes in. I'm breaking the water molecule down, and then the OH is going to get put here on this CH2, and this H is going to get added to the oxygen here, and that'll allow that to break apart. And so here's that OH from the water, and here's the H from the water. So the H2O, right? So one hydrogen went here, another hydrogen, and the oxygen went over here. And I broke that water molecule down in order to break this molecule of acetylcholine into acetic acid and choline. So that is a hydrolysis, a hydrolytic reaction, very common. And then a very special kind of breaking down reaction is what we call combustion. And I want to bring that up. So a combustion is where you have a hydrocarbon, and a hydrocarbon is just an organic molecule that consists of hydrogen atoms and carbon atoms called hydrocarbon, right? So when hydrocarbon combine with oxygen to form heat, carbon dioxide, and water, that is what we call combustion, all right? And these belong to a large group of reactions we refer to as redox reactions. You'll hear this term used a lot. Redox means reduction, oxidation. So when something gets oxidized, oxidation just means that you are adding oxygen or taking away electrons. All right. And when you add oxygen to something, because oxygen is really good at accepting electrons, it's doing the same thing, right? Is taking away electrons. Reduction reactions are when you take away oxygen or you add electrons. So you're reducing the charge in essence, right? If I add a negative charge, I'm reducing it, right? So oxidation is adding oxygen or taking away electrons. Reduction is taking away oxygen or adding electrons. And these are collectively known as redox reactions or reduction oxidation reactions. So this is oxidation here. So when you oxidize a hydrocarbon, you have combustion. You can get heat and energy out of it. So a common example would be octane, right? That's a common ingredient in gasoline. That's C8H18. So when octane is oxidized, so these are the reactants here, okay, that forms carbon dioxide, water, and heat, right? And that explosion, if you will, that results, the heat that's released, that energy can be used to push on a piston, to do work on a piston, and that piston is attached to a drive shaft, right? And that eventually turns wheels, and you can use that to propel a vehicle. Well, a similar kind of reaction occurs in the human body, but instead of octane, what we do is we can combust other organic molecules, such as glucose is a common one. So glucose, my iPad just froze. There we go. So glucose is C6H12O6. Right? It's a type of sugar, or what we call monosaccharide, or simple carbohydrate. So the human body is kind of like a car, but it doesn't oxidize octane, but rather it oxidizes glucose. So when glucose is oxidized, okay, so glucose plus oxygen, carbon dioxide is released as well as water, plus ATP and heat, right? So the body also combusts. So the oxidation of glucose is a combustion reaction. All right. So again, I'm giving you guys examples. So when we look at the energetics of a typical chemical reaction, usually what you're going to get is you're going to have reactants. And let me choose a different color here. There we go. So reactants tend to be a higher energy. And then there's an energy barrier that you have to get over. You can't just put it together and expect something to spontaneously happen all the time. There's generally a barrier. You have to put a little bit of energy in to get the chemical reaction to work. And that little energy barrier is known as the delta E, or the activation energy. So there's some energy barrier that you need to get over before the chemical reaction will proceed. So the reactants, you get over the energy barrier, the chemical reaction occurs, and then you have your products. And typically your products are going to be at lower energy, and so they'll be more stable. Now, it is possible to have a chemical reaction where reactants are at lower energy and the products are at higher energy, but this requires you to put a lot of energy in to get that chemical reaction to work. And these are sometimes referred to as exothermic, right? They actually pull heat from the environment because they take a lot of energy, or they might use a lot of ATP in the terms of the body. Lots of ATP is required for these kinds of chemical reactions. And then the products that are produced tend to break down, right? They're high energy and they want to break down, right? Either way, this energy barrier can be a real problem because this energy barrier means that many chemical reactions are not efficient. All right. And so in the human body, or indeed in most organisms, there is a large group of proteins known as enzymes. And enzymes are proteins that decrease the activation energy. So what they do is they make a chemical reaction more efficient. And this is referred to as catalysis. So enzymes catalyze chemical reactions. They make chemical reactions occur more efficiently. So you might have a reaction look like this before enzyme. So your reactants and products, and you can see that there's a real big barrier. You have to put a lot of energy in to get that chemical reaction to occur. But if enzymes are present, reactant to product, you can see that the energy barrier is very, very small, and the chemical reaction will occur more efficiently. So the enzyme catalyzes the chemical reaction. For example, if we go back up here to bring some pathophysiology in, when we talk about acetylcholine, this reaction, the breaking down of acetylcholine into acetic acid and choline, the termination of acetylcholine's action, right, is very inefficient. It occurs very slowly. And so for this chemical reaction to occur, there is actually an enzyme required, and it is an enzyme that is called acetylcholinesterase. Acetylcholinesterase. And acetylcholinesterase catalyzes or makes the breakdown of acetylcholine occur more efficiently. And there are certain types of pathology where this enzyme can be deactivated. And if acetylcholinesterase gets deactivated, then acetylcholine will not break down efficiently, and you will have sustained action of acetylcholine. And are you all familiar with nerve agent poisoning?
Yes.
Yeah, you learned about that, right? Nerve agent toxicity, organophosphates, carbamates, right? Insecticides, weaponized agents like sarin, VX, taboon, etc. The primary mechanism of action of nerve agents revolves around them deactivating. They actually chemically bind to acetylcholinesterase. They deactivate acetylcholinesterase, and that prevents the body from efficiently breaking down acetylcholine, and acetylcholine remains active. And so one of the things that acetylcholine does is it attaches to receptors on muscles and causes muscles to contract, right? In the neuromuscular junction, that is a primary neurotransmitter. And so when lots of acetylcholine gets released, right, if the acetylcholinesterase isn't there to help catalyze its breakdown, you can get spasms muscles. You can get the muscles that regulate breathing, your diaphragm, your accessory muscles, and can seize up and become paralyzed. You have acetylcholine that regulates secretions in your lungs and your gastrointestinal tract and your eyes and your nose. And so what happens is you get uncontrolled secretion and you fill up with mucus and tearing and fluids, right? And you guys probably learned sludge, right? Acronym to help you remember what happens when you have nerve agent toxicity, right? And salivation, lacrimation, urination, defecation, gastrointestinal upset, and emesis, right? Among other things. And this is why. This is the fundamental pathophysiology of nerve agent toxicity, is the deactivation of acetylcholinesterase, which prevents the hydrolytic breakdown of acetylcholine, right? So you can see that this chemistry stuff actually has direct pathophysiological consequences. And that's just one example of this. All right, are there any questions over any of that stuff? It's kind of the basics of chemical reactions. Everybody okay there?
Yes, sir.
All right, awesome. Well, let's continue moving on now. So now what I want to do is I want to talk a little bit about organic chemistry, and then we'll move in and we'll talk about biochemistry, some biochemical pathways, and even a little bit of pathophysiology relating to those biochemical pathways. So you see, we're just kind of layering stuff on top, right? We're just getting a little more complex, and with each layer and just adding on to your foundation of knowledge. Okay, how are we doing on time? Okay, we'll keep going and we'll take a break here in a little bit. So, organic chemistry. The reason that I want to talk just a little bit about organic chemistry is this is a chemistry where carbon is a backbone molecule. And the reason that carbon is so important is carbon is in group 4, which means it has 4 electrons in its valence shell. So when you look at carbon, you've got 4 electrons, and those 4 electrons can form typically covalent bonds with multiple other atoms, and so including itself. So what you can get is you can get carbon combining with itself, and you can get chains of carbon. And then you can get other atoms that can covalently bond to those carbons. And so you can see that the carbon atoms form the backbone of this larger, more complex molecule, right? That is why it is important, and it is incredibly relevant, because virtually actually all of the large molecules in your body, or what we call macromolecules, use carbon, have carbon that forms their backbone. With the inorganic molecules, help regulate the environment that these organic molecules live in. So the inorganic molecules like water and the various electrolytes, sodium, potassium, and magnesium, and calcium, that's kind of the soup, if you will, the ocean that these organic molecules are floating around in, right? And the complex interplay between the organic and inorganic and the chemical reactions are resulting that ultimately kind of help produce the cells and the tissues and the organs and the organ systems, and ultimately the organism. So we talk about organic chemistry. The simplest organic molecules are what are known as hydrocarbons. All right. And they're just simply carbons and hydrogens, right? So the simplest hydrocarbon is a carbon that is covalently bound to 4 hydrogens. Let me draw that a little differently. There we go. CH4. 1 carbon and 4 hydrogens, right? And what I'm going to do is I'm going to talk a little bit about how some of these are named, right? So the way that we name hydrocarbons is by how many carbons you have in that molecule. If there is just 1 carbon, we call that a meth. 1 carbon is a meth. All right. 2 carbons would be F. 3 carbons would be prop. 4 carbons would be bute, and so on and so forth. All right. And the other part of naming is what kind of covalent bonds are we dealing with? If all the covalent bonds are single covalent bonds, okay, this is what we call an alkane. An alkane is all single covalent bonds. Okay, that's an alkane. And it will end with an A and E, ane. Now, on the other hand, if there is a double covalent bond anywhere in that molecule like that, so 2 carbons double covalently bonded to each other, that is what we call an alkene. And then it will end with an E and E. And finally, if there is a triple covalent bond there, those are called alkynes. So maybe I have a carbon triple covalently bound to another carbon, and it will end with a Y and E. All right. So how many carbons do you have, and and what are the nature of the covalent bonds? So the simplest hydrocarbon is a 1 carbon alkane, right? CH4, but it's carbon, all single covalently bound to hydrogen, right? So CH, all single covalently bonds. So that would be methane, right? 1 carbon, all single bonds, methane. That's where the term comes from, right? Methane. And that's, of course, a colorless, odorless gas that's fairly explosive. It's fairly unstable. Let's talk about another molecule, an alkene. So that's carbon double covalently bound. And then there are hydrogens. So 2 carbons would make an F. All right. And because there's a double covalent bond, it would not be ane, it would be ethene, right? Ethene. All right. And let's just give you an example of an alkyne. 2 carbons triple covalently bound to each other. And then you have a hydrogen here and a hydrogen here. So 2 carbons would make this an F. Triple covalent bond would make that an alkyne. So it would end in YNE, or ethine. And you might know ethane because the vernacular term for ethine is something called acetylene. Acetylene, right? Like oxyacetylene welding. This is acetylene that's used for welding. All right. So those are hydrocarbons. The other term that I want to briefly mention are saturated versus unsaturated hydrocarbons. So a saturated hydrocarbon is a hydrocarbon where you have the maximum number of hydrogens attached to the carbons. That's a saturated hydrocarbon. So if I have, for example, 2 carbons there, if every other covalent bond is occupied by hydrogen, that would be a saturated hydrocarbon. But if I have, say, a hydrocarbon that looks like this, lost some hydrogens to the double covalent bonds, that would be an unsaturated, right? The maximum number of hydrogens are not bound to carbons. So this would be saturated and unsaturated, right? When we talk about like saturated fats, for example, fats are very long chains of carbons, and a saturated saturated fat is where all those carbons have hydrogens, But if you have areas where there are double covalent bonds that take the place of hydrogens, we would call that an unsaturated fat. All right. And then if there's an acid group on the end of the fat, we would call that a fatty acid. A fat's a long chain of hydrocarbons capped off by an acid group. That's a fatty acid. All right. Now what we can do is there are various chemical reactions that can modify hydrocarbons. Okay. And so what you can do is you can take a hydrocarbon and add something called a functional group. A functional group is a small chemical or molecular group that, when added to a hydrocarbon, changes. Alpha means to change. Changes the nature of the molecule. All right. And there are many different kinds of functional groups. I'll talk about some of them, give you some examples. The first functional group is an OH, a hydrogen and an oxygen, or oxygen and hydrogen. The OH group is also known as a hydroxyl group, or the vernacular term, an alcohol. That's what an alcohol actually is. An alcohol is a functional group that gets added to a hydrocarbon to change it into a different molecule. So if I have methane, CH4, okay, so this is methane, right? It's a gas. It's a colorless, odorless, explosive gas. If I replace one of these hydrogens with an alcohol group or an hydroxyl group, all right, so let's do that. I hydroxylate it. I will create a new molecule. I will create an alcohol. I will turn methane into something called methanol. Methanol. The OL tells me that that is methane with an alcohol group. And now, instead of a colorless, odorless, explosive gas, I have a liquid. I have a flammable, toxic liquid, right? Methanol is very toxic. I can do the same thing with, let's see here. Oh, let's take this here. Let's take this molecule here. I want one of you to tell me what the name of this molecule is right here. So there are 2 carbons, and it's all single covalent bonds. So what would you call that hydrocarbon? 2 carbons,
Ethane.
all single covalent bonds. Say it again.
Ethan.
Yeah, you got it. Ethane. Good. So F means 2 carbons. Ane means it's an alkane, all single bonds. So I can take ethane and I will replace one of these hydrogens with a hydroxyl group, and I will create a new molecule. And I will create something called ethanol. Ethanol. What is ethanol?
Gas.
Say it again. So ethane is a colorless, odorless gas, but ethanol is what? Just adding. Say it again. I thought I heard something. What's that?
Alcohol.
Well, it is an alcohol, but alcohol just means a hydrocarbon with a hydroxyl group. What kind of alcohol is it?
Gasoline.
No.
Just some gasoline additive. That's it.
It is added to gasoline, but ethanol is also known as drinking alcohol, right? This is the alcohol that you find in beverages that some people consume. This is the drinking alcohol, right?
ETOH.
Yes, that is the symbol, ET. And now you all know where that comes from. ET is F. OH is the hydroxyl group, making it an alcohol, right? That is why drinking alcohol is symbolized as ETOH. It's ethyl alcohol or ethanol. Does that make sense?
Yeah.
And so hopefully you can see by just adding a functional group, you can completely change the character of a basic hydrocarbon, right? So that is one example, the alcohol group. And alcohol groups, because they have oxygen in them, they tend to make the resulting molecule more polar. So ethane or methane, for example, is a colorless, odorless gas that does not dissolve in water. But if I had a hydroxyl group and I turned it into methanol, now I have a polar liquid that does dissolve in water. So you can see that the human body can use these functional groups and add them or take them away from molecules to make them more or less polar, or to make them react in different ways chemically. That's why functional groups are so important. Another functional group is a CH4. And CH4 is what we call or CH3, excuse me. CH3 is what we call a methyl group. And when methyl groups get added, they tend to make things less polar. So they tend not to dissolve in water. So methyl groups tend to make things non-polar. So they don't dissolve in water as easily, but non-polar tends to dissolve in fats much easier. For example, there is a drug called amphetamine. All right. And what we can do to an amphetamine molecule is I can add a methyl group to the amphetamine, and that will make it non-polar, more likely to dissolve in fats, which means it will tend to go into the brain because you have a lot of fat in your brain, right? The myelin. And so amphetamine gets turned into methamphetamine. That is an amphetamine with a methyl group as CH3 added to it to make it easier to go into the brain because it's non-polar. Again, you can see that a functional group can be used to change the character of a molecule. All right. Another common functional group, as I mentioned before, is something called a carboxyl group. These are also known as carboxylic acids. All right, carboxylic acid. All right. And this is a carbon double bonded to an oxygen, then OH with an alcohol. And what happens is when this group gets dissolved in water, this hydrogen tends to pop off. right? So when this gets dissolved in water, what you're going to get is you're going to get something like this. Hydrogen ion pops off, the proton pops off. So that's what makes it an acid. It's called a carboxyl group, one of the most common organic acids that you're running into, right? And when you have an organic acid, that gets dissolved in water and gives off a proton, when an organic acid gives off a hydrogen ion or proton, its name gets changed. All right. Its name gets changed. I'll give you a couple of examples, right? Acetic acid. Acetic acid, and that has a carboxyl group in it. When acetic acid is dissolved in water and it gives off a hydrogen ion, what's left over is called acetate. Acetate. So acetic acid is acetate after it gives off a proton, right? All right. Let's see here. Let me think of a couple of other lactic acid. That's an important one from a pathophysiology standpoint. Lactic acid, when it gives off a proton, it is called lactate. Formic acid. Formic acid is a toxin. It's actually when methanol gets metabolized, it can get turned into formic acid. When formic acid gives off a hydrogen ion, it becomes formate. All right. So when organic acids do what acids do, their names get changed into an ATE, acetic acid, acetate, lactic acid, lactate, right? Formic acid, formate, and so on and so forth. All right, that's a carboxyl group. All right, we talked about the amine. The amine functional group comes from ammonia, which is NH3. All right. And so whenever you see NH or NH2 or something like that added to a molecule, that is an amine group that has been added to a molecule. These are very common in amino acids, as we talked about earlier. All right. Another functional group that I want to talk about is called catechol. This is also known as benzene, or an aromatic ring. It is actually a ring of carbon atoms. So you've got carbon, 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 carbon. Looks like this. And then what you have is you have kind of this alternating double and a single bond structure. It's called a resonance structure, like this. So you have a ring of carbon atoms with alternating double and single bonds around it. That's called an aromatic ring or a catechol ring or benzene. All right. And this is very nonpolar. And what you can do, you can add these different functional groups too. For example, I can make a very important molecule called a catechol.
Here's what I found.
Stop. A catecholamine. A catecholamine. It's a very important group of molecules. So a catecholamine is a catechol, right? Aromatic ring, all right? And then you have a little carbon bridge attached to an amine. Something like that. This is a catecholamine. So you've got your hydrocarbon here in the middle, and each little point is a carbon atom. You've got a benzene ring here, and you've got an amine here. And this forms a backbone of important molecules in the body like adrenaline, also known as epinephrine, and norepinephrine, right? As well as dopamine, right? Serotonin, or 5,8,5-hydroxytryptamine, this is serotonin, right? So these are all hormones, and neurotransmitters are very, very important, right? So hopefully you're beginning to see the importance of these functional groups. A couple more, you have aldehydes. An aldehyde is just where you have some molecule, and then in the middle of it, you have a carbon double bonded to an oxygen, and then kind of the rest of the molecule. Or actually, no, let me just do that again. So you have some molecule here, whatever, carbons, hydrogens, and then you have a carbon, double bond, oxygen, ending with a hydrogen there. All right, so that's an aldehyde. All right, an example of that, a toxic example of that, since this is a pathophysiology class, is a formaldehyde, right? So that's carbon double bonded to an oxygen, and then a hydrogen, and a hydrogen, right? So that's a formaldehyde molecule. And so you can see this is the aldehyde group there. Let's see, another one is acetaldehyde, which is a common byproduct of certain kinds of metabolism in the body. So that's a carbon, hydrogen, O. So you can see here is the aldehyde group. And then a similar group, but not nearly as toxic, is what we call a ketone. Okay, ketone is similar to aldehyde. So an aldehyde is a COH and then some other stuff, whereas a ketone is a little different. It is a carbon double bonded to an oxygen with other stuff other than hydrogen. So an example of a ketone, the most common one that you'll see in the human body, is something called acetone, right? It's a product of lipid metabolism, breaking down fats to make energy. Acetone is one of the byproducts of that. So you've got let's see here, you've got a carbon double bonded to an oxygen, and then you have a CH3, right? So that would be acetone, right? So that is a ketone, right? So we talked about methyl groups, hydroxyl or alcohol groups, aldehydes, carboxyl groups, amines, and let's see here, and of course aromatic rings or benzene rings, right? So those are all just examples of functional groups that can be added or taken away from hydrocarbons to make more or less complex molecules that have different chemical properties. All right. So any questions over that? Because I think it's high time for another break. Anybody have any questions?
No, sir.
All right. So what I'm going to do is let's take another break. Let's see, what time have we got? It's 11:03. Let's meet back up at 11:15. I will see you all at 11:15. That'll just help us out next week. Let's see, got something in chat. Okay, got that cleared out. All right, so I think we're ready to move on and talk about the macromolecules of life now. These are the larger, typically more complex molecules that make up the cells. And these are made up of organic molecules and their functional groups. So let me go ahead and broadcast this and go back into the notes here. All right, so the major macromolecules of life. There are 4 major categories of these larger, complicated molecules that make up the cells. Okay, these include what a group of molecules known as the carbohydrates. These include the fats or lipids. These include the nucleic acids. And these also include a protein. So these are the 4 major categories of macromolecules of life. So let's just start off talking about the carbohydrates. All right. So the carbohydrates, also known as sugars, carbs also known as sugars. All right. These are hydrocarbons. They're made of carbon, hydrogen, and oxygen. And they have a hydrogen to oxygen ratio of 2 to 1. So there are 2 hydrogens for every oxygen, right? So these are hydrocarbons with a carbon or with an oxygen to hydrogen ratio of 2 to 1, right? And there are different types of carbohydrates, sugars. These are also known as saccharides. All right. And if you have just one sugar, which tends to have a kind of a ring-like structure by itself, it's called a monosaccharide. And if you have 2 sugars combined, they're called disaccharides. And then if you have 3 or more, they're called polysaccharides. All right. And typically, the human physiology needs a monosaccharide. So if you have long polymers, oligosaccharides of sugars combined together, something like starch. So starch is a long chain of monosaccharides, and starch is how plants store sugars. The starch has to be chopped up into monosaccharides, and that's part of digestion, right? When we digest carbohydrates, we have enzymes, and an enzyme, remember, is protein and that ends with ASE. ASE tells you that you're dealing with an enzyme, and there's an enzyme called amylase, and that breaks down these complex carbohydrates, these starches, into monosaccharides, right? So we can then absorb them and use them. Now, humans or animals also can store sugar. If you have excess sugar, we don't create starch, but rather we create something called glycogen. So glycogen is where you have excess glucose and the body combines glucose molecules into a long chain, a long polymer called glycogen. And then if we need to rapidly increase our blood sugar, right, there is a hormone called glucagon that gets released, and then glucagon causes glycogen to be chopped back up into monosaccharides to glucose. So glucose is a monosaccharide that we can use, and glycogen is the complex polymer where we combine a bunch of glucose together, right? And then we can chop it back up, right? So what is important? What else are carbohydrates or saccharides important for? Well, they're important for several reasons. They are an energy source, right? Through combustion, we oxidize them to create energy, ATP. That's the primary role. They also play a role in metabolizing, right? You can actually add sugars to other molecules, and sugars are pretty large and can make molecules easier to dissolve in your blood, and you can get rid of them in your urine. So you can combine other substances with sugars to make them easier to get out of your body. That's something called glucuronidation, for example. But primarily, they play a major role in energy source. Sugars are attached to the surfaces of cells. This is called glycosylation, and they can help with receptor function and things like that. All right. That's a major role of sugars. The next major category I want to briefly talk about are the fats or lipids. And the fats, lipids, are almost always in the form of what are called long chain fatty acids, at least in the human body, right? So the common structure is something called a triglyceride. A triglyceride. So essentially what you have is you have a glycerol head. And then you have 3 long carbon chains that come off of that. So every little bump on that is a carbon atom. I'm just kind of simplifying it. And then each of these really long carbon chains ends in a carboxylic acid. Right? So the glycerol, the long carbon chain, and then the acid, right? That is a triglyceride, a long chain fatty acid, right? Is the common chemical structure. And then these can be modified to form other molecules, but that's kind of the basic molecule. So where are these important? Well, these are important because they can form a long-term energy storage. Fats can actually be converted into fuel for your cells. There is a cycle, a biochemical pathway in your body. It's called beta oxidation. Beta oxidation. Essentially what beta oxidation does is it chops the long chains up into small chunks. And then those small chunks can be ultimately fed into biochemical pathways that produce energy. And that's called beta oxidation. These fats are oxidized into a substance called acetyl-CoA and other chemicals that can be fed directly into energy producing metabolic pathways in the body. So they do act as a long-term energy storage. Although if you have to break down a lot of fat to produce energy, there are different wastes that are released. There are ketones that are released, like acetone, and there are also organic acids that can be released, as you might imagine, right? Because you're liberating carboxylic acids here. And this form is the pathophysiological basis of a diabetic condition referred to as diabetic ketoacidosis, or DKA. You all hopefully have heard of that. And in diabetic ketoacidosis, you have a situation where the body does not produce insulin. And remember, insulin is the molecule attaches to a receptor on the cell surface and facilitates the movement of glucose into the cells. Glucose can be converted to ATP, right? It can undergo cell respiration. It can be combusted, oxidized into ATP. If you don't have insulin, you don't make any insulin, you can't do that, right? And so what the body has to do is the body has to start breaking down fat to produce energy, right? And so fats get broken down through beta oxidation, and you end up releasing a lot of acetone and a lot of organic acids. And that's where you get acidosis and you get the ketones, because as we talked about earlier, acetone is a ketone. And that's where the term ketoacidosis comes from, right? So there's also a lot of pathophysiology surrounding fatty acid, abnormal fatty acid metabolism, all right? Let's see here. In addition to this, fatty acids are also needed to make certain kinds of hormones. They're what we call steroid hormones. A steroid, so most of you are familiar with the term steroid, but steroid literally means a hormone that comes from fatty acids. So fatty acids get converted to hormones. And so these include things like testosterone, estrogen, progesterone, right? All of your sex hormones are steroid hormones, right? And so you do need fat, you do need the acids, and in fact, this happens in women. This is part of what goes on, but in biological women who have very low body fat, generally less than 10%, sometimes what will happen is their menstrual cycle will stop. They will stop menstruating, or their whole cycle will cease to function because their fat is so low, they're not able to produce the steroid hormones they need, among other things, right? So there's some pathology there as well. And these fatty acids are critical in forming the cell membrane. Remember, the cell membrane consists of a phospholipid bilayer. So what you have in the cell membrane is you have phosphate, that's PO4. You have these phosphate heads on the outside and the inside of the cell, and the phosphate is polar, so it can interact with water, but you have lipid tails that form the middle of the plasma membrane, and the lipid tails are nonpolar, right? So this is nonpolar here. These long carbon chains are nonpolar, and so they interact with each other and they turn inward, right? They don't like to be around the water. They are what we call hydrophobic, right? And so we need fatty acids to form the phospholipid, specifically the lipid part of the cell membrane, right? Fats are also important because they can help protect different organs and structures in the body. But there are also other problems with fat. If you have fat going places where it shouldn't go, or you have certain parts of the body being turned into fat, that is a pathophysiological process known as steatosis. Steatosis is where something becomes fat, and a common area where this occurs is in the liver. And there's a fairly common disease that is known as non-alcoholic fatty liver disease. And the basic pathophysiology of that is the hepatocytes the cells of the liver begin to get essentially turned into fat. They are actually replaced by fat lipids. And this is steatosis. And so this is sometimes called non-alcoholic fatty steatosis. And so normal cells get turned into fat, and then that causes lots of inflammation. And the liver becomes inflamed, and the hepatocytes begin to fail, and you can actually have liver failure result, right? So this is fatty liver disease. Something similar to this occurs in something called cirrhosis of the liver. You get the inflammation and you get the fat formation, right? So there are good things, bad things, right? So fats are essential. There are lots of essential things. And then of course there are lots of pathology associated with fats as well. Fats can also deposit and form plaques on the inner surface of blood vessels, for example. And this is something called atherosclerosis, right? Where you get an accumulation of fats and other things like calcium that can cause narrowing of blood vessels. You can also get this with the carbohydrates as well, specifically with glucose. When you have high levels of sugar in your blood, abnormally high levels of sugar cause inflammation in blood vessels. And over time, this can cause lots of inflammatory dysfunction, right? And this can be very toxic to organs, right? And we see people with diabetes, for example, diabetics who have poorly controlled blood sugar. If their blood sugar is very high, right, those high levels of blood sugar will tend to cause inflammation of blood vessels, right? And that can accelerate atherosclerosis and arterial sclerosis, which is a hardening of blood vessels. This can be toxic and cause inflammation in the kidneys and cause renal failure. This can be toxic to nerves and cause neuropathy, where you have nerve dysfunction and you can lose sensation, or you can get pain, or you can get numbness and tingling in your fingers and your toes. You can also lose circulation to your hands and your feet, and you can be prone to developing ulcers and infections. And this can be toxic to the nerves in your eyes, and it can be toxic to other parts of your eyes, and you can have visual dysfunction. All right, so that's if you have uncontrolled blood sugar over the long term, right, as well as uncontrolled levels of lipids, fat. Specifically, a type of fatty acids known as LDLs and VLDLs. Those stand for low density lipoproteins. We haven't talked about proteins yet, but we will, in very low density lipoproteins, right? Low density, they're small and they're easy to kind of clog things up. Whereas your high density, your HDLs, right, tend to be easier to clear and tend not to clog things up, if you will. All right, so those are the lipids, or the fats, or the fatty acids. Let's talk about the nucleic acids. So let me ask you all a question. What is the important role of nucleic acids?
DNA.
Does anyone know what
It's
what
DNA.
are nucleic acids?
Proteins.
Can you all hear me?
Yes, can you hear me?
Yes. Can you hear us?
Say that again. I'm sorry.
Can you hear us?
Yeah, I can hear you. I think I just had a little hiccup there. Could you say that again? I missed it when I asked what are nucleic acids. I'm sorry.
Someone answered it's DNA. Someone else answered that it is proteins.
Okay, so they're related to proteins. Yep. So a lot of people, yeah, think of DNA. And what is the role of DNA and other nucleic acids in the body? Like, what's the whole purpose of that?
It's in cell development, cell growth, and reproduction.
Yeah, moving in the right direction. Yeah. So nucleic acids, think of them as information. This is information. These form the quote unquote blueprint for cells, right? So this is the information required to produce a certain kind of cell and to have the cell do what it needs to do. All right. And so typically, and this is not specific to all organisms, but we're going to specifically talk about what are called eukaryotic organisms. Eukaryotic organisms are organisms that have a well-defined nucleus in the cell. There are other organisms called prokaryotic organisms like bacteria, archaea that do not have a nucleus, and they are a little different. But eukaryotic organisms have a nucleus. And then within that nucleus, the blueprint or the genetic material for that cell is contained in that nucleus. And it's all wrapped up in a very complex structure. And these large structures of wrapped up genetic material that contains information are known as chromosomes. All right, chromosomes. And does anyone know how many chromosomes there are in the human?
23.
Anyone have? Say that again.
23.
It might be related to 23.
Someone said 46.
46, yeah. So there are actually 46 chromosomes. 46 chromosomes inside of the nucleus. And half of those chromosomes, or 23, come from your mother. And then the other 23 come from your father, right? For a complete set of 46 chromosomes. And you have two general types of chromosomes. You have your sex chromosomes, and these are the chromosomes that form the basis of your biological sex. And then you have all of the other chromosomes, and those are referred to as autosomes. So your sex chromosomes are the X's and the Y's, right? And then your autosomes are all the other ones, all right? So does anyone know what sex chromosomes make a biological male?
X.
Why?
Both X and Y.
What? Yeah, so a biological male has one X and one Y.
So we're the tripod. So we have dick.
So
Sorry.
that would be biological. That would be a biological male, right? An X and Y. All right. What about a biological female?
2 X's.
XX makes a biological female. Now there are some, some genetic disorders. We'll talk a little bit about genetic disorders a little later on in the course. But this is just normally what we would see. Good. And then all of the other chromosomes are what we call autosomes. So when we see that somebody has an autosomal genetic disorder, that is a disorder of genes in one or more of the autosomes. But if we say that somebody has a sex-linked genetic disorder, that is a disorder involving genes of the sex chromosomes, right? So that's just some really basic genetics there to prime you for when we talk about it in more detail a little later on. Okay, now within these chromosomes, we have information for making proteins. That's primarily what we see, is information for making proteins contained within chromosomes. And so you have your chromosome, and then a little chunk of that chromosome that codes for a specific trait. All right. Maybe it's an eye color, for example. So it's a very specific trait is referred to as a gene. All right. So a gene is a section of a chromosome that codes for a specific trait. So is everybody okay on the difference between genes and chromosomes? Does it make sense?
Yes.
Excellent. So the basic chemical structure of nucleic acids is as follows. There are three things. The first thing is you have a 5-carbon sugar. Now, the kinds of sugar that we use for energy are 6-carbon sugars. So like glucose is a 6-carbon sugar, fructose, but these are 5-carbon sugars, right? So these are what we call pentose sugars. So these are very special kind of sugars, right? These are pentose. In fact, there's a metabolic pathway that the body uses to produce these sugars. It's called the pentose. It's called the pentose phosphate pathway, or the hexose monophosphate shunt. Right? Those are the same thing, right? That's the metabolic. That's a metabolic pathway that cells use to make these sugars. All right. So you have those. And then you have a phosphate group. And then you have something called a nitrogen base. All right. And so it looks something kind of like this. You have a strand. So you have a sugar. And then it is attached to the phosphate. And then you have a sugar. And you have a phosphate, all right. And then you got maybe the end here, right? That's one end. And then this other end ends in a alcohol or a hydroxyl group. And then attached to these sugars, you have what are called base pairs. These are also known as nucleic or not nucleic acid, but these are what we call these are the nitrogen bases, and these form the code. And in humans, you have essentially you have in DNA, at least. We'll talk about DNA versus RNA, but in DNA, which we mentioned earlier, you have 4 different kinds of base pairs. You have adenine, you have guanine, you have thymine, and you have cytosine. And adenine can only combine with thymine, and guanine can only combine with cytosine. So the way that this works is in one part of the strand attached to the sugar, let's say that I have an adenine. So adenine on the other strand do this again. There we go. On the other strand, there's the sugar and OH. So the OH is on the top instead of the bottom. Adenine, on the other side, I would have to have a thymine. And then those two would interact hydrogen bonding, right? So AT. And then if I had a G here, all I could have was a C over here. All right, like that. So what you can do is you can create a code. So let's say that I have like an A, C. So the complement to that would be T, T, G, right? And so on and so forth. And it is this code of base pairs that makes the code for traits in proteins, right? Encoded within the A's, the T's, the G's, and the C's are the instructions for making proteins, right? Now, what we do is these instructions are all wrapped up in these chromosomes, and these chromosomes are wrapped around protective proteins called histones, and it's all packed in there and protected, right? And so you can think of this as a blueprint, but here's the question. Let's say that you want to build a house. Would you take the original blueprint of the house to the construction site? Would anybody want to do that? What do you all think?
You want a copy, right? Protect the original.
You want to keep the OG. You want to keep the OG blueprint protected, right? And just make a copy of it and bring the copy out to the work site, and then we can go off the copy and it'll tell us how to build the house, right? Same thing with the cell. So the OG material, the OG code is what we call DNA, deoxyribonucleic acid. And that stays within the nucleus, all nice and protected. And what happens is if the cell needs to make a protein or do something, right, the DNA gets unraveled, and then there are special proteins that come in and copy the DNA, right? The helicase kind of helps unwind it, and you can copy it. And the DNA gets converted into something called mRNA or messenger RNA. And RNA stands for ribonucleic acid, right? And in ribonucleic acid, the structure is very similar to DNA. One of the major changes, however, is that in DNA, adenine complements thymine and guanine complements cytosine, but in RNA, adenine is complemented by uracil as opposed to thymine, and guanine cytosine. So thymine is replaced by uracil in RNA. So it's not an exact copy, but it's the same information. So the messenger RNA can go out of the nucleus And then the messenger RNA runs into a machine within the cell called a ribosome. And the ribosome reads the code, the instructions of the RNA, and then that creates a protein. All right. So the copying of DNA getting copied into RNA is what we call transcription. And then the RNA getting turned into a protein is what we call translation. Right? So the RNA is translated into a protein. All right. Does that make sense? Everybody okay there? Does that make sense? And this is sometimes
Yes, sir.
referred to as the central dogma of molecular biology. And we say dogma somewhat sarcastically, right? Because there's really not such a thing as dogma in science, like we talked about yesterday. We could always be wrong. But essentially what this says is that there's one direction: DNA, RNA, protein, right? That's the main direction. Now, there are certain cases where the direction can go the other way, but that's abnormal, that's pathological. And one example of this involves certain viral infections. Certain viral infections, there are certain viruses that when they infect your cells, some of these viruses infect your cells with RNA. Now, under normal circumstances, RNA cannot go into the nucleus, right? RNA can't go to DNA. It can only go into the ribosomes and get turned into protein. However, some viruses have special proteins that are enzymes that actually catalyze and enable the RNA to get turned into DNA, and that DNA can actually get inserted into the genome, the genetic material of your cells. And an example of a virus that can do this is a virus that contains a protein called reverse transcriptase, right? And that makes sense, right? It's an enzyme. It is reversing transcription. And viruses that contain reverse transcriptase are known as retroviruses. Retro means to go backward, right? And does anyone know the classic example of a retrovirus? It's one that we have been fighting for decades now.
Is
AIDS?
it AIDS?
No.
Polio?
No. You all familiar with this?
HIV.
HIV. Somebody mentioned AIDS. Is AIDS HIV?
No, AIDS is what infects the body and then causes HIV.
No. Actually, I'm glad I brought this up. This is super important, actually. So, HIV, this is important. HIV is the virus, okay? So when we say somebody has HIV, that means that the HIV virus, which is a retrovirus, which contains reverse transcriptase, which allows its RNA to be converted into DNA, right? When you get infected by HIV, we say that you have an HIV infection. Everybody okay with that? Now, when that infection damages your immune system, when there is a sufficient amount of damage to your immune system where you become immunosuppressed because HIV infects cells, specifically helper T cells in your immune system, right? and it causes suppression, immunosuppression. When that occurs, then we say that you have AIDS. AIDS stands for acquired immune deficiency syndrome. AIDS is the disease that HIV causes. Does that make sense?
Yep.
Okay.
Yes.
The reason I bring that up is we are currently dealing with a pandemic of another disease that is caused by a virus. So when we say that somebody has COVID-19, is COVID-19 a virus?
Yes. Yes.
No. No. COVID-19 is not a virus, just like AIDS is not a virus. COVID-19 is the disease that is caused by the SARS-CoV-2. So SARS-CoV-2, SARS stands for severe acute respiratory syndrome. CoV stands for coronavirus 2. So SARS-CoV-2 is the virus, okay? And the disease that that virus causes is COVID-19. COVID-19 stands for coronavirus disease 2019. Okay. Does that make sense?
Yes,
Chris,
sir.
Yes.
Okay. Yeah, go ahead. Sorry.
sorry to go back a little bit, but when going back to the retrovirus,
Yes. Mm-hmm.
what's that called? The reverse trans what?
Reverse transcriptase. Reverse
Transcriptase?
transcriptase. Yes, that is the enzyme that that these retroviruses contain, and that enzyme allows the messenger RNA within the retrovirus to be converted into DNA, and then it gets inserted into the DNA of your cells. Otherwise, if you just dump a bunch of RNA into somebody, that RNA cannot get into the nucleus and it cannot be turned into DNA, right? Only with reverse transcriptase can that occur. That's why we call these retroviruses, because they go backwards in the opposite direction of the central dogma of molecular biology. Does that kind of make sense?
Yes.
Cool. Now, there are other RNA containing viruses that are not considered retroviruses, but they can do the same thing. But they use a different enzyme. For example, SARS-CoV-2, right? Is SARS-CoV-2 a retrovirus? What do you all think?
No.
No, but can it do the same thing that retroviruses do? Because coronaviruses are RNA viruses, but they use a different enzyme. They do not use reverse transcriptase. They use a different enzyme. So they can do a similar thing to retroviruses. They just don't use the reverse transcriptase enzyme. Does that make sense? You guys okay? Okay with that, or?
Yeah.
Yes, makes sense.
Okay, cool. Yeah. Now there are also other viruses that are DNA viruses, and if it's a DNA virus, then the DNA can just go right into the nucleus. All right. So hopefully that makes sense there. All right. So that is the introduction to the nucleic acids, and then finally we have the proteins. Whoops. The proteins. Super important macromolecules. So proteins come from amino acids. We talked about those, right? Amino acids. You have different types of amino acids. You have a couple dozen that are important for humans. And remember, amino acids contain an amine group, a central carbon with some chemical chain that comes off of it, and then a carboxylic acid. And you can combine these amino acids and you can make long chains of what are called polypeptides, right? And so when you have an amino acid, 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 right? You combine them and you create this long chain, this polypeptide, and that forms what we call the primary structure. So the primary structure of our protein are these peptide bonds of the individual amino acids. And then what happens is as the amino acids, as these polypeptides get long enough, the group that come off of the alpha carbon here begin interacting with one another. So you have intermolecular forces. What happens is that long chain begins to fold and twist. And then that produces the complex structure of the protein. So the primary structure is just this amino acid, these sequence is the sequences of ATGCs that, or in the case of RNA, it's the AUGCs that tell the ribosomes, okay, I need this amino acid combined with this, combined with this, combined with this, combined with this, right? And then a certain combination of amino acids will cause the polypeptide to turn and twist in a very specific way. And then that will produce what we call the secondary structure. All right. And you get two major types of secondary structure. You get folded sheets that will fold on top of another, like sheets. And we call those beta sheets. Or it can twist around in a helical structure, kind of like how DNA or RNA is, and we call those alpha helices. All right, that's the secondary structure. All right, and then what happens is these sheets and these helices can begin interacting, and they fold even further into the tertiary structure. And then you get this tertiary structure of these sheets and helices, and you can get several of them that form these globules, if you will. And then these globules themselves will start interacting, and they will come together to form the quaternary structure of the protein, right? And that is the complete protein. So something like hemoglobin, for example, is a good example of a quaternary structure protein. So it contains 4 globulins, 4 large chains. You've got 2 alphas, and 2 betas, and then they all can come together to form the hemoglobin molecule. And then each alpha has and each beta has a little core where you have an iron that is held in place by nitrogens. That's called the porphyrin ring, and that's actually where the oxygen molecule interact, right? So you can see you start off with relatively simple structure, the primary structure here, the peptide bonds, and then once that polypeptide gets long enough, it begins to fold in on itself and actually produce more complex levels of structure. And in fact, this is one of the greatest problems in molecular biology, is something called the protein folding problem, is trying to predict protein folding, because if we could, that would allow us to make incredibly complicated molecules, and be an incredible breakthrough. But it's so complicated, we don't really understand it all that well. We're using a lot of like machine learning and algorithms to try to predict protein folding. But the exact folding is so special that shape plays a critical role in protein function. And the specialized shape that is associated with a certain kind of function is what we call conformation. And every protein will have multiple conformations. And that is a certain shape that imbues that protein with a certain function. And if the shape changes, the function may change, right? And so you can have different molecules and atoms interact with a protein, cause shape to change just a little bit, and you'll what's called a conformational change. And that protein may work differently, or it may stop working, or it may start working. And if the shape changes so much that the protein quits working, that is sometimes referred to as denatured. We have denatured the protein and it has quit working. And this is easy to demonstrate when you cook something. If you eat a piece of meat and you cook it, what happens? Does it just completely fall apart when you cook meat, which is a lot of protein? Does it completely fall apart?
No.
No, it hardens up, right? It'll harden up, but the primary structure of the meat is still there. It tends to hold itself together, but it'll harden up, it'll brown. So what you've done is you've denatured it by cooking, but the primary structure, the peptide bonds that hold the primary structure, are still intact because they're very tough bonds. But what you've done by cooking, by heating it up, is you've disrupted all of these intermolecular forces that are responsible for the secondary, tertiary, quaternary structure of the proteins in that meat, right? The disulfide bonds and the hydrogen bonds and the van der Waals forces and all those intermolecular forces. You can see this with an egg, right? Right? I could quote unquote cook an egg without heat, right? If you take a very strong concentration of ethanol and you drop an egg, like take Everclear, right? Something that has a high concentration of ethanol in it, and you crack an egg and you drop the egg in there, that egg will begin to harden up and cook. It'll look like it's being cooked. And it literally is. It's not being by heat, but it's being chemically cooked. And the alcohol is denaturing the protein in that egg and cooking it, right? And it will look very similar to if you put it on a hot plate and cook it, right? This can also happen in the human body, right? All the proteins in your body, and where are proteins? Where do we see them? They have many roles in the body. Proteins act as enzymes that catalyze chemical reactions. Proteins act as receptors on the surface of cells and within cells. They act as channels to allow ions and water and other molecules to move in and out of cells. They act as mobility and transport, right? They're literally proteins inside of your cells that like they look like they have little feet, and as ATP hydrolyzes and breaks up the little feet of these proteins, and it can actually walk along the cytoskeleton of your cell and transport stuff around the cells, right? So proteins have so many critical roles. And if the environment within your body is altered, right, that can induce conformational change in all these proteins and sometimes indeed, right? For example, if the pH of your body becomes too acidic or too alkalotic, that can then interact with different proteins in your body and can induce conformational changes, and they will quit working. A good example of this is hemoglobin. Right? Hemoglobin. If you have lots of hydrogen ions in your body, so that means that the pH is low, right? Because a low pH equals a high hydrogen ion concentration, right? They will chemically interact and they will change the conformation of hemoglobin. And what they will do is they will prevent hemoglobin from binding oxygen. They will actually cause hemoglobin to release oxygen, and then it will not bind onto oxygen, right? And then in a highly alkalotic environment where you have very few hydrogen ions, the opposite occurs. Hemoglobin binds very tightly to oxygen, but does not want to release oxygen, right? Temperature as well. Temperature will impact how hemoglobin works. But it's not just hemoglobin, it's many other proteins, right? For example, many different proteins that are involved in blood clotting, right? If your body temperature gets too low, there will be conformational changes in clotting factors. They will quit working. You won't be able to coagulate. You will become what we call hypercoagulable, or actually, no, you'll become hypocoagulable. You will not be able to clot efficiently, right? And so people who are hypothermic tend to be more prone to bleeding because the low temperature induces conformational changes in their clotting factors that prevent them from working. So the heat, temperature, the chemical environment, right, all of these things can cause proteins to act very differently, right? And so that is just critical when it comes to understanding basic pathophysiology, and that's why I wanted to spend a little bit of time talking about protein and just general protein structure and function. So before we wrap things up today, are there any questions? Anybody have any questions? Because I know we've gone over an incredible amount of information. So anybody have any questions?
None here.
No? Okay, excellent. So what I'm going to do is let me stop sharing. You all are going to have some homework. So let me just show you what that homework is real quick. And then we will conclude class for today. And you guys can have a well-deserved weekend. All right, so I'm just going to screen share here real quick. All right, let me wait for that to pull up for you all. All right, so if you go to the home page in the modules view, go down to the Chemistry of Life module. Now, in the Chemistry of Life module, there are 3 things that you all are going to need to do this weekend. First of all, there is a quiz that is due on February 7th. It's a short quiz, and it's a pretty basic quiz. It's not like super complicated information. So make sure that you complete that quiz by the due date. The other 2 things that that you're going to need to do, there is a short read here a short reading assignment. It's only like a page or two, and it's very simple. And it is on something called ROS, or reactive oxygen species and free radicals. And these are a very important category of molecules that are very damaging to cells. And these molecules are produced when there is dysfunction, when there's cellular dysfunction and different metabolic pathways are not working, and you have anaerobic metabolism, for example, you can have an accumulation of these reactive oxygen species and or free radicals. And so I want you to read on that. And then there is a video, it's about half an hour long, and it's just a real high yield video. And what it does is it will cover the major metabolic pathways in the cell. All right. And what we've done over the last couple of days is we've developed the foundation for understanding these pathways in some more detail, right? And these are going to include pathways that are critical for energy production in the cell, things like glycolysis, things like the Krebs cycle, things like the electron transport, things like the urea cycle and the Cori cycle, right? And so this is just going to be kind of a basic rundown of those. And so I want you to go through those videos. And then on Tuesday, we will cover those concepts and then transition into talking about fluid and electrolyte and acid-base imbalances. So we'll actually get into some hardcore pathophysiology, if you will, next week. So up until that point, we're just kind of building the foundation up, the biochemical foundation for understanding dysfunction. So are there any questions over what you all are going to need to do this weekend and what we're going to start doing next week? Anybody have any questions over that?
What would
No.
be some good stuff to review for that chemistry life quiz?
The chemistry of life quiz. So everything that we've covered in the last 2 days.
All right.
Yeah.
And then,
So
for like chapters 8 and 9, are we still reviewing chapter 8, or should we jump to 9, or what's the...
so yeah. So you have the syllabus, right?
I do. It
Okay.
starts with chapter 8, but it seems like more that we're covering, it seems to be like in chapter 9.
Not really. Like all the stuff that I've covered is mainly really anatomy and physiology, and I've thrown in a little bit of pathophysiology, but basic cell structures and the nucleus and DNA and RNA and proteins and carbohydrates, all that stuff's actually more chapter 8, right? The anatomy and physiology. Whereas chapter 9 is focusing more on the actual dysfunction, right? Which was what we'll get into next week, right? I think chapter 9 starts off with like the cellular response to stress and injury, edema, electrolyte imbalance, acid-base imbalance, and that's all stuff that we're going to focus on next week. So a lot of what we talked about in the last couple of days has been more chapter 8 stuff. So that's where the chemistry of life is really going to be more about, what are cations and anions, and what's a difference between a covalent and a ionic bond, or what's a metallic bond. So it'd be real basic questions, not super complex, not super detailed, just to kind of make sure that you have a basic understanding of things. And obviously, I'm not going to be watching you take the quiz. So if you want to use your notes to help you out, or the book to help you out, you can. I believe it's timed, so you don't want to run out of time, but definitely use resources to help you if you need. Think of the quiz as more of like a review, if you will, of some of the concepts. Does that make sense?
Yes, sir.
Okay, great. Cool. Excellent. Any other questions? Anybody have any other questions?
No, sir.
All right.
No
well,
questions.
then I will see you all on Tuesday. So Monday during office hours, I'm actually going to be with the other paramedic class. I'll be reviewing a block exam with them. So if you need to get a hold of me for some reason, shoot me an email and we'll see about arranging some other time if you need to get a hold of me on Zoom. Otherwise, I'll be doing an exam review with the other class on Monday during office hours. But I will see you all Tuesday morning at 8:30.
Okay, thanks a lot.
Thank you all. Take care.
Thank you, Chris.
Thank you. Take care,
Thanks,
everyone.
Chris.
Thank you. Be safe, everyone.